Hi, everyone. Welcome to our talk, AutoSphere. I'm delighted to tell you something interesting about WAF bypassing. In this talk, I will show how vulnerable WAFs are, allowing attackers to cause splendid damage. Okay, I'm Zhen Qingqu, a graduate student at Zhejiang University, and Xiang Ling is a research associate at ISCS, and Chunming Wu, my supervisor, is a professor at Zhejiang University. And this is the agenda of our talk. Firstly, I will introduce the background of our talk, including web attacks and WAF. And secondly, I will introduce the traditional methods and existing tools that are commonly employed to bypass WAFs. However, I will show the shortcomings of these tools. And thirdly, I will introduce our attack framework, AutoSphere. It can be used to generate SQL injection payloads to bypass the target WAF efficiently and effectively. Then I will present some results of AutoSphere against the 7 commercial WAF as a service from mainstream vendors. And as a responsible researcher, I will detail our vulnerability disclosure progress. And finally, I will conclude this talk. Okay, let's begin. In this part, I will introduce some background. As we all know, web services are being exposed to worldwide threats with various methods. Here are the top 10 web security risks. Among them, injection is one of the most dangerous attack methods. With injection attacks, hackers can send untrusted payloads to the web service, and they can steal information or take control of the underlying system. Except for SQL injection and cross-site scraping, the JNDI injection is also a crucial attack method, which is the exploit method of Log4Shell. In this talk, I will use injection attacks to present this talk. And to mitigate malicious requests like SQL injection, the Web Application Firewall, aka WAF, is one of the most widely used and effective defensive systems. Normally, WAF is deployed in the front of the origin server, indicating that any requests from clients must be detected and filtered by this WAF. Only requests that are detected as benign will be forwarded to the origin server for further processing. And generally, WAF can be categorized into 2 types, that is the signature-based WAF and the machine learning-based WAF. The former one is traditional but effective. It takes advantage of various rules predefined by domain experts to detect and block malicious requests. Recently, motivated by the greater success of machine learning, a variety of machine learning-based WAFs has been proposed and implemented. Moreover, with the development of cloud computing, WAF as a service, as one kind of security as a service, has been proposed to facilitate the deployment, configuration, and update of the traditional WAFs. The administrator who manages web services only need to redirect their requests from clients to the interfaces of WAF as a service provided by vendors, so that the malicious requests can be detected and filtered before sending to the origin server. And here I will employ a funny example to illustrate how frequently WAF is used in the cloud. When I submitted my session content, I was blocked by the Cloudflare used by blackhat.com. Then I had to change my content to avoid being blocked by this WAF. Okay, so above are the backgrounds. Here, I will introduce some WAF bypassing methods, including manual and automatic ways, and their shortcomings. As WAF need to trade off between the false positive rate and the false negative rate. WAF cannot rudely intercept all suspected malicious requests. This condition gives attackers an opportunity to perform attacks. And attackers can bypass a WAF in many ways, such as at the architecture level. He can just access the origin server, or he can send his payloads in chunks. Today, we focus on the most common and universal way. That is, we can mutate the original payload. As shown in this example, we can generate the original payload and test the generated payloads by changing the case of letters or just adding some comments. A natural question is, how can we automate this progress of generating and testing? Are the existing tools or methods usable? Firstly, I will introduce some semi-auto tools. With Ninja provides a single point fuzzing test for SQL injection and cross-site scripting. With it, we can further test. We can perform a fuzzing test with the SQL injection payload, which continuously replaces fuzz with values in the database. However, even if we find a valid keyword, WAF will still block the entire payload after being inserted to the entire payload. And some sophisticated attackers may consider a multi-port fuzzing test after constructing its original payload. It may be effective sometimes, but attackers need to manually specify the keywords and the replacements before each attack. It requires domain expertise and is laborious. Besides, this method is similar to brute force search. It is inefficient. And SQL Map, as an excellent SQL injection testing tool, comes with many WAF bypassing template scripts. When using SQL Map, an attacker can specify some scripts, such as equal to like, random comments, or uppercase. However, attackers need to choose templates manually, just like that. And SQL Map cannot select them intelligently. Besides, multiple templates cannot work well together. The templates can only mutate all locations within the payload. The above work present valuable concepts of semi-auto WAF bypassing. Next, I will introduce some latest research on fully auto WAF bypassing. Firstly, Dimitri et al. Proposed the WAF-AMO. It is a tool that can avoid machine learning-based WAF. They first predefined 7 string-based SQL injection payload mutation operators like key swapping, comment injection, and operating swapping. Afterward, they employ a priority queue-based optimization method to guide the mutation progress. Specifically, WAF-AMO repeatedly mutates the initial payload multiple times to generate several payloads. Then it selects the payload with the lowest merge score as the initial one for the next round until it bypasses the target WAF or reaches the termination condition. And inspired the work of evading malware detectors with reinforcement learning. Wang et al. Proposed a WAF evasion framework with the reinforcement learning approach. After training, the reinforcement learning agent can select an optimal mutated operator according to the current state of the SQL injection payload. And in fact, they have followed the mutated operators in WAF-AMO. Besides, Hemtai et al. Improved the work from Wang in several aspects, including expanding their the mutation operator space, and they have defined some state based on the fast text embedding model, and so on. However, the above work has some shortcomings. According to the Chomsky hierarchy, the string-based mutation method in above works cannot fully cover the attack payloads. That is, it may miss some key parts of the payload when generating adversary payloads. Specifically, here is a code snippet of a mutation operator in WAF-AML. It can search for tautology in the payload and replace it with other types of tautology, such as mutator 1 equals 1 to 1 does not equal 2. However, if we add a space next to the equal sign in the payload, WAF-AML will not recognize it. Besides, WAF-AML may invalidate the entire payload. For example, it may mutate the R-like into R-equal. And at the same time, the priority queue is the optimization method and the reinforcement-based method are not suitable for attacking real-world WAF, as their output is binary. Besides, the gradient-based optimization in adversary machine learning is also not suitable for our problem space attack. To sum up, it's imperative to devise a generously semantic preserving mutation method. We should preserve the original functionality and maliciousness of the initial one. Besides, we should design some optimization method suitable for black box attacks. It should be training free and it can generate two different WAFs. Okay, in this section, I will introduce our proposed framework, AutoSphere. It can automatically bypass and inspecting the target WAF. Normally, a HTTP URL consists of 4 elements. That is the scheme, the domain name, and the path-through file, and the parameters with multiple pairs of key and value. As the process of SQL injection attack is limited to the parameter values and keep other paths unchanged. Because that, we should generate SQL injection payloads based on the original one. Therefore, AutoSphere should not only to be limited to the payload of the original SQL injection, but it also ensures that the generated SQL injection has the same functionality and maliciousness as the original one. To handle it, according to the different roles of different parts in the original SQL injection, we divide the original SQL injection payload into 3 modules. That is the left boundary, the query, and the right boundary. And we further limit the attack surface of AutoSphere to the query part. Both the boundaries, the left boundary and the right boundary, are restricted to unchanged, so that the functionality of the original SQL injection is preserved. The query is a core module and is needed to be further processed. Small. Instead of simply treating the query as a sequence of strings, we further represent it with a hierarchical tree. We argue that on the basis of the hierarchical tree representation, we can perform one fine-grained and customized processing for each node according to their unique characteristics and constraints. I think it could facilitate the generation of adversarial SQL injection payloads. Besides, we propose a weighted mutation strategy based on the context-free grammar. We can use it to generate a set of candidate adversarial SQL injection payloads, and the generated payload keeps the same functionality and maliciousness as the original one. We formulate the CFG grammars for each semantic type of the SQL injection hierarchical tree. For example, as shown in this figure, the tautology of 1 equals 1 in node 2 can be transformed by context grammar into a Boolean expression that turn out to be true, or tautology in other formats. And we can mutate the SQL injection payload at the atomic level without breaking the original semantics. That is, we can keep the same functionality and maliciousness. and with the above tree representation and the context-free grammar. In addition to carrying the mutation operators in existing methods and tools, we propose several novel and practical mutation operators according to the latest tech blocks. And we employ the Monte Carlo tree search algorithm to guide our searching process, that is combining the mutation replacements of each node. The Monte Carlo tree search is to continuously build a search tree where each node represents a state of the SQL injection hierarchical tree, and the edges correspond to transformations. Okay, here is an example. After a few rounds of the game, we select the current best child of number 2 with passes 3b and 5a. Specifically, 3b is to mutate the white space in node 3 to comment 4, and 5a is to mutate equal in node 5 to inline comment. Afterward, we perform an expansion progress, that is randomly selecting 4a and generating the number 3 as a child of number 2. Then we finish this round of game by simulation, that is randomly mutating multiple times by reaching the limit. At this time, we interact with the target WAF to obtain the current classification result of the malicious confidence score and update all parent nodes based on the number of visits and the result from the WAF. And in the end, we output the payload corresponding to the final state of the Monte Carlo search tree. Here is the final generated payload. Okay, now I will present the results of AutoSphere against the 7 commercial Wi-Fi as a service from mainstream vendors. Besides, by performing several case studies, I will analyze and inspect some general deficiencies of Wi-Fi as a service among these vendors. We first manually constructed about 100 SQL injection payload of common methods, including union-based injection, error-based injection, and blind injection. And these payloads are used to verify the semantics of the generated payloads. Then we found 2 commonly used datasets from Kaggle and GitHub. These payloads are used to evaluate our attacker success rate. Okay, firstly, to compare the semantics of the payload before and after mutating, we first deploy multiple runtime environments as shown in this page, such as database in multiple versions and backend scripts in Python and PHP. And by observing the execution results of the payloads, we can prove that AutoSphere will not invalidate the generated payloads. That is, all payloads generated can maintain their original semantics. Okay, then we deploy 7 WAFs from these vendors, that is AWS, Fortinet, F5, Cybersecurity Cloud, Volume, Cloudflare, and Model Security. And we send our payloads to them with 4 commonly used request methods. Specifically, as our modified backend web service support 4 commonly HTTP request methods, that is GET, POST, and their JSON types. We fine-tune the mutation process in AutoSphere to preserve the semantics across different request methods. That is, for example, the /n should be encoded as a %0a for non-JSON requests, and the hash sign cannot be presented in comments when sending the payload via GET. Okay, here are the results. Firstly, it's the false negative rate. The FNR directly reflects the protection effectiveness of WAFs. Alarmingly, both the AWS and Cloudflare have FNRs of over 60% on the Kaggle dataset. That is, more than 60% of malicious requests will be directly forwarded to the backend service. Further, we can divide the WAFs into 4 categories based on their response to different request methods. For example, the Cloudflare implements different strategies based on whether the request is via GET or POST. And AWS processes the payloads separately according whether the request parameter is in JSON type. And the model security processes requests via getJSON separately. And here are the attack success rate, the ASR. ASR illustrates the robustness of WAF against adversarial attacks. Our attacks against WAF as a service in the cloud is successful. The ASRs against AWS on the Kaggle dataset even reached 99%. Besides, we can find that when requesting web service in JSON type parameters, ASRs are much higher than non-JSON. It's a greater security risk given the current deployment trend of web services. That is, more and more web services are designed based on the decoupled architecture, most of which use the JSON to transform data. And if a WAF shows high FNRs and ASRs, it evident that the protective effect is unsatisfactory. If the FNRs of WAF is low, but the ASRs are relatively high, it means that the WAF cannot defend against well-structured adversarial attacks. The ASRs of each WAF has a similar distribution to FNRs, which led to the following conclusion. For example, the 4 WAFs hosted on AWS are less capable of preventing SQL injection. The volume is effective because it has low FNR and ASR both. And Fortinet has ASRs many times higher than FNRs, which means that it cannot defend against adversarial attacks very well. However, we must stress that the above results and rankings are obtained with our limited settings and samples. It cannot fully represent the actual defense effects against all samples in the wild of these vendors. And here I will play a short video to show the out-of-box attacking effect of AutoSphere. Okay. Here we first deploy web service on DW on AWS EC2. And then we create a load balancer to access the web service. Here we can access the web service. That's a normal request. And now we attack the web service by SQL injection. 1 = 1, it is. And then we can steal some information from the website, such as the database name, and the column name. Sorry, it's the table name. Here is the column name. And even we can steal the data in the database. Here are the encrypted password. We can decrypt it. And the above attacks are against the unprotected website. Now we enable and configure the AWS WAF. First, we create a access control list. And add our load balancer. Then we add some rules provided by AWS. For example, the call rule set, the no-embedded inputs, and the SQL database. All of them are used to prevent SQL injections. Okay, we have opened and configured the AWS WAF. Now we re-attack the payloads. Okay, the WAF is on. Here is the original payload. It is blocked by the AWS WAF. All payloads are blocked, and the normal request still works. And now we use AutoSpear to attack the AWS WAF with 3 simple steps. Firstly, copy the URL of the target WAF. That is the target web service. And secondly, write the desired payload to the configuration file. And finally, just run the script. We can find that within several seconds, all the payloads are attack successful. Okay, here are the generated payloads. Let's test them one by one. Here is the original one. It is blocked by the AWS WAF. And here is the generated one. Okay, now we can bypass it. Okay, WAF can be bypassed successfully. And we have found that all the generated payloads that can bypass the AWS WAF are being added some control symbols. We can manually add some control symbols to bypass the AWS WAF. Just a session can let me load the file from the password of the system. And we can even write a web shell to the target web service. Okay. Here is a PHP info. And we can execute the system terminations. WMY is admin. And the directory is DVWA. Okay. Let's continue. Here are more examples. We select 3 representative payloads which can steal table name, column name, and sensitive information from the protected website. Just like in the video, we can replace white space with control symbols like the /t session, we can bypass the AWS WAF. And furthermore, just adding a comment or turn DML into inline comments, we can bypass the F5 and the Cloudflare. And as above, commercial WAFs are black box. We further investigate the exact reason of bypassing by monitoring the audit logs of model security. The model security is built and deployed by us. Take the SQL injection payload as an example. We need to buy the two engines at the same time. That is the semantic analysis engine and the regular matching-based engine. You can find that just adding select 0 all, we can bypass the label injection. And adding a comment, we can bypass the model security completely. In summary, this case studies further verify our conjecture. Windows detection signatures are non-robust, causing several vulnerabilities. And based on the hierarchical trees during attacking, we present the effective mutation method for WAF as a service in the cloud. Can see them in this table. For example, just adding some comments, we can bypass 4 WAFs and specific payloads. And lucky attackers can manually using these conclusions to bypass some WAF. However, the effective mutations for specific WAFs and different payloads are unique. That is, only a combination of multiple mutations for specific locations takes efforts. That is, Autosphere is much more effective in bypassing the mainstream WAF as a service solutions, because this WAF as a service has vulnerable detection signatures for both semantic matching and regular expression matching. And now here are the feedback from mainstream vendors. We reported our findings to the affected vendors by submitting vulnerability reports and contacting their technical support staff and security researchers. Up until now, F5, Cloudflare, and Vaulm have mitigated the frauds, and the other 4 are still working with us, as the frauds we found cannot be easily patched. And for example, the security incident response team of F5 have mitigated the frauds reported by us within 1 month, and they have added our names to their official website. Okay, to sum up, we have proved that WAF as a service from mainstream vendors can be bypassed in a fully automatic and intelligent manner. And specifically, we propose Autosphere, which utilizes a semantic-based mutation strategy and a heuristic searching strategy suitable for black box attacks. And we have summarized various underlying methods of WAFs in the wild and their actual defense effects based on our limited samples and sightings. In addition, we disclose some general bypass patterns that defenders can use them to improve their products. Okay, thank you for your attention. I will now take some questions from the audience.
Thank you very much. The first question is from Jiangyu Zhang. He's asking how do you configure this WAF in your evaluation? And are they all in default settings?
Okay. Thanks for your valuable question. In fact, we have deployed. We have deployed our own websites and databases on the Google Cloud platform and protecting them utilizing these 7 WAFs in turn. The WAFs are following their default configuration, specifically for the AWS, Fortinet, F5, and the Cybersecurity Cloud. These 4 require manual rules configuration, and we have enabled the call rule set that is suitable for protection against the OWASP top 10 attacks, and there are advanced rule set for SQL injection.